You grew up believing that electricity lives inside the wires, like water in a pipe. You flip a switch, electricity rushes through the copper, reaches the bulb, and boom, light. Simple, clean, comfortable, and very incomplete. People explained it to you like this so you could pass exams and remember formulas. But if you really want to understand what's going on, the way a physicist like Richard Feynman would push you to understand, that picture is not enough. It hides what is actually happening in the space around the wires. It hides the real story. Let's start with something basic. Your phone is at 5%. You plug in the charger. Somewhere in your walls, there are copper wires. Somewhere far away, maybe tens or hundreds of kilometers away, a giant turbine is spinning in a power plant. Metal is moving inside magnetic fields. And somehow that motion ends up as your battery climbs from 5% to 80% to 100%. What is really traveling from that power plant to your phone? Is it little balls of electric stuff flowing inside a tube, or is something else happening that nobody really explained to you? Before we go into the walls and the power lines, I want you to do a tiny experiment in your room. It looks silly. It is simple, but it quietly breaks your old picture. Take a plastic pen, or a small strip of plastic tape. Rub it hard on your sleeve or in your hair for a few seconds. Now bring it close to a small piece of paper on the table. Don't touch it. Just bring it close and watch. The paper moves, it jumps, slides, and then sticks to the plastic. No battery, no plug, no wires, just plastic and cloth. You didn't turn on electricity, you just rubbed something, and now this piece of plastic can reach across empty space and pull on matter. We usually shrug and say, "Oh, static electricity, I learned this in school." Then we forget it. But if you slow down for a moment, this is actually insane. You are watching one of the four fundamental forces of the universe act right in front of you. The same force that holds atoms together. The same force that keeps your hand from going through a table. The same force that lets your brain send signals, your muscles move, and your eyes see. What really happened when you rubbed the plastic is this. You moved electric charge. Some electrons were scraped off one material and collected on the other. The plastic now has a tiny extra amount of negative charge. Your sleeve or your hair has a tiny extra amount of positive charge. The total amount of extra charge is small compared to the number of particles there. Maybe one extra electron out of a trillion. That sounds like almost nothing. But the electric force between charges is unbelievably strong. If you take two electrons and hold them 1 centimeter apart, the electric repulsion between them is not just bigger than gravity. It is something like a number with 42 zeros times stronger than the tiny gravitational pull between them. For charged particles, gravity is basically a joke. The electric force is the serious one. So when you create even a tiny imbalance, a few extra electrons piled on that plastic, the electric field around it becomes strong enough to reach through the air and pull on light pieces of paper. That field is real. It fills the space around the plastic. It is not just in the plastic. It is in space. It pushes and pulls on charges in other objects. Notice that in this story, we didn't use a single wire, no socket, no copper. Electricity here is not in a wire. It is charged and the invisible electric field in space. That is your first clue that the simple school story is not the full truth. Now zoom in to the level of atoms. Every atom has a small, dense center called the nucleus. In that nucleus sit protons with positive charge and neutrons with no charge. Around the nucleus, in a fuzzy cloud, lie electrons with negative charge. Opposites attract, like charges repel. They do this with enormous force. If these forces are so huge, why doesn't your body fly apart? Why doesn't everything explode from all that repulsion? Because in ordinary matter, positive and negative charges are almost perfectly balanced. For every proton, there is usually an electron. Their forces cancel out like a perfect tie in a tug of war. The electric forces are still there, but on average they add up to 0. When you rub the plastic, you disturb that balance a little bit. You create a region where there is a slight excess of one type of charge. Suddenly, the hidden force becomes visible. Your arm hair stands up. The paper jumps. You sometimes even see a spark. That spark is just charges trying to rush back into balance. Static electricity is the same force as the one inside atoms, just less balanced and easier to see. There aren't two different electricities. There is one electromagnetic force showing itself in different ways. Now ask a deeper question. What does it actually mean to touch something? You feel the table under your hand. You feel the phone in your grip. It feels like your skin is in direct contact with the atoms in these objects. That's how your brain imagines it. But that's not what's really happening. When your hand presses a table, the atoms in your skin and the atoms in the table never let their centers, their nuclei, get close enough to really collide. Instead, the outer electrons around those atoms get pushed close together. Because they have the same type of charge, they repel very strongly. That repulsion pushes back on you. You feel resistance. You call it solidity. But it is really electric repulsion between electrons in your hand and electrons in the table. Think about what that means. Every time in your life you felt something solid, pushing a door, holding a mug, pressing a key, standing on the floor, you were feeling electric forces. You have never touched anything in the way your instinct tells you. You have only ever floated on electric cushions, so already electricity has escaped the wires. It is not just a thing in metal. It is what makes matter feel solid. It is what makes your world feel like a world of objects instead of ghosts. The wires in your wall are just one special place where charges move easily. But let's go back to those wires, because that's where your old picture really breaks. Picture a simple circuit. A battery, some copper wire, and a small bulb. You connect the wires so they form a loop. You close a switch. The bulb lights up. The usual story is electrons leave one side of the battery, flow through the wire, through the bulb, and then go back into the other side of the battery, like water circulating in a pipe. This picture is not completely wrong, but it is very misleading. First, the electrons don't move fast. In a typical metal wire, the electrons are already there, like a crowded room full of people. When you connect the battery, they start to drift slowly. Their average speed is something like a fraction of a millimeter per second. Very, very slow. If electricity were just electrons leaving the battery, running down the wire and reaching the bulb, your light would take a long time to turn on. But it doesn't. It turns on almost at once. So what moves quickly? Not the electrons themselves. The thing that moves quickly is the change in the electric field. When you close the switch, the battery creates a voltage difference across the circuit. That sets up an electric field all along the loop, almost instantly. That field pushes on the electrons everywhere in the wire at the same time, like a signal. The electrons don't need to travel from the switch to the bulb. They were already sitting in the bulb's filament, waiting. The field arrives, they feel the push, and they begin to move. Think again of a long line of people standing shoulder to shoulder. If you gently shove the person at one end, that person does not run to the other end of the line. They move a tiny bit and bump the next person who bumps the next, and so on. The wave of motion moves quickly, even though each person moves only a small distance. That's how it works in a wire. The signal, the change, the push can travel fast, even if each electron moves slowly. But there is an even bigger twist. Where is the energy actually flowing? You probably picture the electrons carrying energy inside the wire, like trucks carrying cargo on a road. This is where the electricity in the wires story really fails. In the more complete view, the energy that lights the bulb does not travel inside the copper itself the way water travels inside a pipe. It flows through the space around the wires in the electromagnetic field. Here's how to imagine it. Around any charged object, there is an electric field. Around any wire carrying a current, there is also a magnetic field wrapping around the wire. When an electric field and a magnetic field are present together in the right way, energy flows through space. There is a clear direction for this energy flow. Physicists can calculate it. But for now, just picture this. The battery sets up electric fields around the wires. The moving charges create magnetic fields. Together, these fields carry energy from the battery through the space around the circuit into the bulb. The copper wire is not a pipe full of energy. It is more like a guide. It tells the fields where to go and where to be strong. The real river of energy is in the invisible fields outside and around the wires. If you could see them, it would look like streams of energy flowing beside the wires, curving in toward the bulb and pouring into its filament. This is why the old picture is incomplete. It puts everything important inside the wire. The real story says, look outside the wire, into the field. Now stretch this picture across the whole power grid. In a power plant, huge turbines spin. They might be turned by steam from burning fuel, by falling water, or by wind. These turbines spin magnets inside coils of copper wire. As the magnets spin, the magnetic field through the coils changes. A changing magnetic field creates an electric field. That electric field pushes on electrons in the copper. They start to move. Their motion creates more magnetic fields. These fields stretch out into space, around the power lines that leave the plant, running across the landscape. Far away, where those lines come into your city and then into your house, transformers and wires are arranged so that the fields there push on charges in your local wires. Energy is guided down into smaller and smaller circuits, into your room, into your charger, into the tiny parts inside your phone. All along this journey, no electric fluid is being poured from one place into another. Instead, fields are being set up and changed, and charges in different places are responding. A transformer is just a device that uses this idea directly. It is two coils of wire, often wrapped around a piece of iron. When current in the first coil changes, the magnetic field in the iron changes. That changing field passes through the second coil and creates an electric field there. That electric field pushes on electrons in the second coil, and current appears in that coil. Nothing has crossed the gap except a changing field. The coils have never touched. The conversation between them is silent and invisible. It happens entirely through the electromagnetic field in the space between them. A radio antenna works the same way, but at a distance. Charges in the transmitting antenna are driven back and forth. That motion shakes the electromagnetic field and sends waves out into space. Those waves reach the receiving antenna. There, they push on charges in the metal and make them move. That motion is then turned into sound or data. Again, no wires connect the two antennas. The only link is the field. Even light itself is just this same field behavior in pure form. Light is an electromagnetic wave, electric and magnetic fields changing in time and space, supporting each other and moving forward. When light hits your eye, it shakes electrons in the atoms of your retina. That triggers chemical changes and electrical signals in your nerves. You call that seeing. Inside, it is still electricity and fields doing their work. So now, put all this together. The force that holds atoms together, the feeling of touch, the light you see, the spark from your sweater, the current in a power line, the signal from a Wi-Fi router, all of these are different faces of the same thing, the electromagnetic field and the charges that respond to it. The The simple line, electricity in the wires, hides all of this. It makes you think electricity is just current flowing inside copper, like water flows inside a pipe. It makes you forget that the real game is being played in the space around the wire. It makes you miss the fact that when you flip a switch, you're not just letting electricity out of the wall, you're reshaping fields that can stretch across cities. 200 years ago, none of this was clear. People saw lightning and static and magnets and little shocks, but they did not know these were connected. Bit by bit, through experiments and deep thinking, we discovered that electric and magnetic effects were part of one unified story. We learned that changing electric fields make magnetic fields, and changing magnetic fields make electric fields. James Clerk Maxwell wrote down equations that captured all of this. Those equations predicted that waves of changing fields would move at a speed that matched the measured speed of light. That's when it became clear. Light itself is electromagnetic. Richard Feynman loved this point. He liked to show that physics is not just a bag of separate tricks, but a small set of deep ideas that explain many different things. For him, electricity was not just what's in a socket. It was a window into how the universe really works. If you only think of electricity as something traveling inside wires, you miss that window. So what is electricity really? It isn't a magic fluid. It isn't a glowing thing trapped in copper. Electricity is what we call it, when charges move and fields change in a way that we can control and use. It is our way of grabbing hold of the electromagnetic force and telling it what to do. Turn this motor, light this bulb, carry this message, store this energy. The story you were given as a child, electricity lives in the wires, current flows like water, is not useless. It's a good first step. But if you stop there, you miss the deeper and more beautiful truth. The truth is that you live in an electromagnetic world that only pretends to be mechanical. Solid things are electric. Touch is electric. Light is electric. Nerves and signals in your brain are electric. Your devices are just the most obvious examples. The next time you plug in your phone or flip on a light, don't just think electricity is flowing in the wires. Instead, try to see the hidden version. A turbine is spinning far away, magnets are moving, fields are changing. Energy is flowing through space around cables and transformers, guided by metal but not locked inside it. That energy pours into your room, into a tiny circuit, into a battery, into the atoms of your device. Charges move a little. Fields change. Screens light up. Signals travel through your nerves. You see, you think, you act. That's why electricity in the wires is an incomplete story. The real story is bigger, stranger, and much more powerful. The world is made of fields, charges, and the quiet, constant push and pull between them.